It is my pleasure to introduce the awardee for the Mike Kirkby Award. For the Mike Kirkby Award, the ESPL editorial board decides on the best paper published in Earth surface processes and landforms. Hello, everyone. It is my pleasure to introduce sorry, there are multiple windows. Here we go. The Michael Kirkby Award is for the best paper published in Earth surface processes and landforms in 2019. And this year, the award goes to Catriona Thompson and her colleagues for their paper Wave Impacts on Coastal Cliffs. Do bigger waves drive greater ground motion? In this citation, it reads, not only is this paper an exemplary demonstration of the power of new geophysical methods, notably environmental seismology, for monitoring geomorphic processes, it also provides fundamental and new understanding of cliff erosion mechanisms. It shows that how waves break as they approach the base of cliffs impacts dramatically upon the intensity of resultant ground motions and hence erosion potential. So it's my pleasure to introduce Catriona Thompson.
Okay, hello, my name is Catriona Thompson. I'm going to give you a bit of a rundown of my PhD research, focusing a lot on the results I published in a paper in ESPL last year, and then a bit more about the continuation of that work. So looking at wave impacts on cliffs, specifically looking at individual wave impacts on coastal cliffs. So a bit of background first of all into why we did this work. So cliffs occur along a lot of the world's coastline. A study by Young and Frilly that came out last year estimated about 50% of the world's coastline was likely to be cliffed. And down here in New Zealand, as you can see in this map, there's a lot of cliff lines. And because people like living in the coastal margin, there's a lot of infrastructure close to the cliff top. So it's really important to understand cliff erosion and how that might change in the future in the context of climate change. So changing wave conditions, changing sea levels, how that might change the wave-induced cliff erosion. But there's still quite a lot of uncertainty around how that happens. So the exact way that waves result in erosion, those mechanisms are not well understood. And that's because it's quite difficult to link them. But we do know that waves do cause cliff erosion in some way. So both by direct wave action of waves interacting with the cliff face and also abrasion, combined with weathering processes, and subaerial processes like physical, chemical, and biological erosion. That's why we get cliff retreat. And where waves do interact with the cliff face, we know that hydraulic action, so that direct wave action, is an important driver of erosion. And that's what's going to be affected a lot by climate change. But because of a lot of different processes that combine to produce cliff retreat, and then a lot of the time the failure that you see is very episodic, and it's sort of a culmination of a lot of different things acting over time. It's really complex, and it's difficult to link the exact sort of drivers of the erosion with the erosion that we see. So to sort of influence the role that each of those erosion processes play. But we wanted to try and figure out a bit more why or how waves are important. And that's because a lot of work out of engineering on wave impact types on vertical structures. So coastal structures like seawalls and offshore structures like floating platforms have found that wave impacts on those walls can lead to failure because of the impact pressure of the waves hitting that structure. And that's because depending on the wave impact type, the shape the wave makes when it impacts the wall, so whether it's breaking, broken, or unbroken, it has a different force associated with it. So you can see here, it's breaking for broken, breaking with a gas pocket impacts, and then unbroken impacts. And that's important because it controls how much energy is also dissipated before reaching the wall. But that sort of investigation hasn't been done on cliffs, on like a natural cliff. But it's incredibly important because if we have a look here at a breaking wave example, you can see the wave is overturning, it traps a gas pocket, which is then compressed against the wall, and we get a big spike in impact pressure there. So we wanted to see if that was the same, if that was also applied to cliffs. And another sort of key reason why we did this work was because there was an increasing amount of work using seismometers on cliffs to measure energy, wave energy that was reaching the cliff. Starting in with Adams et al. 2002, finding that depending on the sort of wave action, the cliff would move in different ways. So if it could detect waves breaking in the foreshore and infragravity waves, and sort of adjustments with tide. But importantly, it could detect direct wave impacts on the cliff face, which made the cliff shake at a high frequency. So we could use seismometers as a sort of proxy for what the waves were doing when they reached the cliff. And we can see sort of a lot of papers subsequently sort of found the same thing or similar relationship, where an increase in offshore wave height and an increase in the water level or tide at the cliff base led to an increase in energy reaching the cliff on average. So looking here, this is hourly energy. You can see that general trend, but you can also see that at higher tides and the water level's higher, for relatively small waves, and the offshore wave heights weren't so big, you still get a lot of energy reaching the cliff. So we wanted to see what was special about those waves in being able to impart so much energy, but not being really big waves. So what was more efficient about those waves, and if it was because of the impact type, the way that it impacted, whether it was broken, breaking, or unbroken, if that was an important control on what the cliff response was. So sort of overall, big picture, what we wanted to do was better link the hydraulic action, which we know is important for cliff erosion, to the sort of cliff response we see using seismometers. We have found that there was quite a good proxy for wave energy, and sort of inserting wave impact type into that situation, seeing if wave impacts were the sort of missing link in why the cliff movement, the shaking could be so different, sort of regardless of the wave height that produced it. So first of all, we did a little bit of a pilot study just to check that you could see individual wave impacts in a seismic record, and that was using some data that came out of San Diego, and we could. And then the main deployment was in Taranaki in New Zealand, and we put instruments out for a month, and we collected the water level and wave data using pressure sensors at the cliff toe and also on the beach in front of the cliff. We had a couple of seismometers buried at the cliff top to record the shaking from the wave impact. And we had a camera along shore to actually record the wave impact. So this is the setup from the top of the cliff. The seismometers are up here, or there was a buried up here, and then we had seismometers here, pressure sensors. And then the camera was mounted on a fence looking along shore so we could see the impact itself in real time. And it kind of looked like this in the field of view. So we could kind of definitively say what the wave impact was. And a key part of this was the camera setup, which was connected to a GPS. So it had GPS time, which meant it could be synchronized exactly with the seismometers. And also it was connected to the internet. It was a network access camera. So we could remotely access the camera and schedule when it could turn on and off so that it was recording at tide levels when there was waves reaching the cliff during daylight hours. So whenever there was water at the base of the cliff, it was recording video. So bearing in mind the sort of categorization that we wanted to apply of looking at broken, breaking, and unbroken waves, and a sort of key part of that is energy dissipation or lack thereof prior to reaching the cliff, and also for breaking waves, the compression of a gas pocket as the wave overturns and then impacts on the cliff. So first of all, we just wanted to check that our data was quite similar to sort of previous studies doing a similar thing by looking at the hourly sort of metrics, the averages of the energy reaching the cliff through time. So on the left here, you can see that that's generally what we found. High tide and at when the waves were the biggest, so up to 3.7, 3.8 significant wave height, you had the highest hourly mean ground velocity. So the shaking of the cliff was biggest when that was the wave conditions. But if we wanted to focus more on what an individual wave impact was doing, we had a look at the peak in the ground velocity over an hour, assumed to be the sort of peak shaking that was reached by an individual wave impacting on the cliff. And for that situation, we actually see that the shaking, the cliff shaking, was highest at high tide again. So when there was water at the higher tide, water at the base of the cliff, but when the waves weren't as high, so they were fairly moderate waves. HS was 1.5 meters for the biggest peak shaking, and you get a lot of sort of these orange-red circles down through here where HS is about 1 meter. So, you know, why was that? Why did we have a lot of ground motion when the waves weren't exceptionally big? And this is during a big storm, but this was similar ground motion, well, bigger peak in the ground motion, but for smaller waves. So we categorized a bunch of waves. This is 8 hours, for example, of data where the video was watched and every single wave impact was categorized by if it was breaking, broken, or unbroken. So A to E are the 5 hours of data when the biggest peaks in the ground motion occurred, and then our F is during storm. So when the HS was 3.7 meters, it was a lot bigger than these other hours of data. And you can see that in general, those breaking waves, the red triangles here, are tended to have higher ground motion, more shaking than broken waves and unbroken waves. And then during the storm, we actually didn't get any breaking waves at all, which makes sense because the wave was so big, they all broke before reaching the cliff. And if we want to hone down on that even more, we compare these 2 hours. Hour E, when the HS was 1.5 meters, that's when the highest shaking event happened in the month-long deployment. Whereas, which is this little triangle up here, whereas during a storm, where the HS was in this hour 3.7 meters, the waves are all broken before reaching the cliff, so the ground velocity was much lower. So here we saw that sort of regardless of the wave height that produced it, it was because the wave was breaking that we had such a big peak in the ground velocity. And if we have a look at the wave itself that did that, we can see just there, that was the wave impact overturning, compressing a gas pocket and going up on the cliff. And then if we have a look at the storm hour, we get a wave broken, it comes in, impacts, and the shaking event is much lower. So from that, we wanted to go even further in looking at the influence of wave impact. So we divided the categorization from the broken, breaking, unbroken into 8 different wave classes. Still broadly under broken, breaking, and unbroken types, but with a more detailed, more sensitive categorization process. So we had 2 types of broken wave, 1 and 2, depending on the breakpoint. Basically, this is all as the breakpoint moves closer and closer to the cliff, the wave impact class changes. We had 4 different types of breaking waves, so 3, 4, 5, and 6, 4 types of breaking waves. And importantly, wave class 4 and 5 have trapped a gas pocket between the wave and the cliff, which gets compressed right against the cliff. And then 7 and 8 are both unbroken wave classes, so they haven't broken at all. They've never started to show, and then get reflected back from the cliff. And if we look at those 8 wave impact classes, and this time we watched a lot more videos. So in the end, this is 7,447 individual wave impacts that were categorized over the month of data collection. And we see that for each of those individual wave impacts, if we plot the peak displacement that those individual wave impacts cause, we get a nice sort of increase and decrease as it goes from broken through different types of breaking, and finally to unbroken waves. And especially if we look at those 4 and 5 wave impact types, which has the nice gas pockets compressed against the cliff, those had the highest peaks in the ground displacement across the different types. And then even further, if we extract the signal, the seismic signal, for those 8 different wave impact classes, and we sort of generate spectral signatures of those wave classes, we can see they've got quite different power spectral densities depending on the wave class that they were. We can see here, again, it's 4 and 5 followed by 3, which is another breaking type, that have the biggest sort of peaks in that power spectral density relative to broken or unbroken waves. And if we then take those spectral signatures from the individual wave impact, we can have a look at getting an idea of the energy transfer that those wave impact classes tended to impart on the cliff. So taking an integral of those signatures, we can get a sort of sum of the energy across all the frequencies to get an idea of the sort of sum of energy that was impacted into the cliff for that impact. And again, what we see is wave class 4 and 5, followed by 3 and 6. All breaking waves, especially breaking waves with a gas pocket, had the highest total energy transfer over the impact relative to broken and unbroken waves. So, very quick overview of that research. But sort of our summary findings were that we could sort of definitively say, using video, what the wave impact was doing, which meant that we could better link sort of response that we saw in the cliff to the wave action that caused it, using wave impacts as a sort of key determinant as to why we saw different responses, rather than just looking at wave heights. And that in doing that, it wasn't just the biggest waves that caused the biggest ground motion, it was actually breaking waves, especially breaking waves with a gas pocket, so those class 4 and 5 wave impacts that caused the biggest shaking events. And when we looked at the sort of spectral signatures of those sorts of impacts, we also saw that they had the highest energy transfer for those impacts. So they were more efficient at transferring that energy by impacting like that, sort of regardless of the energy available because of the wave height that caused them. Thanks. Thanks.
Fantastic. Thank you very much for that. We are open for Q&A questions. This one comes from Mike Kirkby himself. Can everyone hear me okay? Catriona, can you hear me all right?
Yes, I can hear you.
Wonderful. So Mike Kirkby asks, does that mean that if sea level rises, fewer waves will break and impact energy reduced?
It really depends on the site that you're looking at. Where you might have a lot of breaking impacts now, say, and you get a big increase in water depth at the cliff toe, then you might move out of being able to have those breaking waves. But then in some places where you don't have breaking wave impacts at the moment, and you have a bit of an increase in the water level at the cliff toe, then you might move into seeing more and more of those. So it kind of depends on what your current situation is, if it's possible to kind of move into being able to get a lot of breaking waves or not. So some places you'll get more, sometimes you get less. It depends.
I might have missed it in the, did you get a distribution of essentially, over the month that everything was running, the sort of relative proportions of essentially the waves doing the most work when they were, I mean, I know sometimes it was dark, but did you get a sense of how often the gears were really turning at that cliff toe?
Yeah, it was a bit, but because it obviously when we actually knew what the wave impacts were, it was only when we had video for it, so it was kind of slightly biased. sample where it was when there was waves impacting. So you were more likely to, and it was like sort of mid to high tide when that was the only time you kind of could get breaking waves. But basically there was about 1 to 2 hours before and after high tide, pretty much every tidal cycle was when you got breaking waves. And there's some other sort of work we're doing at looking at the sort of distribution across tidal cycles to see how, as the water level does change, you get a different distribution in the different wave impact types. And it kind of just moves through a dominance of each one.
One more for you. And that was that, so there's some of the coastal cliff work that I'm familiar with anyways. It's one of my favorite ideas of the beach as a tool. And I was wondering if if there's more work to be done in terms of taking not just what the wave activity is doing, but combining that with sediment transport, that's sort of, you know, the waves working sediment into this equation as well.
Yes, we didn't look at abrasion or sort of any erosion process that wasn't wave impacts. And so we kind of can't say whether one or the other is a big driver. Obviously, where this site, there was a beach on the shore platform, and that part of the cliff face is mudstone. So you'd assume there's some work happening from sediment in the water column. So yeah, I definitely think it's a factor, but we didn't measure it.
We had just a couple of other questions come in, both sort of related to how you were maybe able to, or whether you were able to link cliff retreat to these impacts, and like were you linking it? Were you able to see that these impacts were opening up joints and bedding planes to weaken the face? And then sort of related to that, I think, is, you know, when you classified the wave types, were you looking at all 7,000 waves, or was there an automated process for that? Are you half blind for video analysis?
Yes. Yeah, so for the actual, linking it to retreat, we did a couple of just LiDAR scans of the cliff face, but obviously when you're looking at, you know, one wave at a time, you can't scan in between each one to sort of actually get a idea of what did what. So I think the next work I'd like to do is to have a longer sort of collection of data and have a more, so sort of better idea of what waves are doing what in terms of the actual retreat or any changes in the cliff face that you see. So the waves, yeah, it was all manual. We did spend a bit of time trying to automate it, but turns out mudstone and water is kind of similar colors to a computer. So yeah, I watched them all and I decided what wave was what.
Well, thank you very much for your time and being with the webinar today and for presenting your work. It's really exciting to see. Congratulations on the award. And
thanks so much.